Hi, let's take a look at an example of the relativistic phenomenon of time dilation. Now, for a proper observer of time, time will pass normally for you within your reference frame. But if your frame of reference is moving relative to another reference frame, then the passage of time for an observer outside of your reference frame is going to appear to be different. And the way to find proper time, someone measuring a proper time interval is measuring that time interval where the clock is stationary relative to that observer, where that observer is seeing the two events occurring at the same location in space, measuring the time interval between those two. So, say you end up driving in late to work one day, and you're traveling at a speed of about 30 meters per second on the drive-in, which is a little over the speed limit of 65 miles an hour in most places. Well, you are moving relative to the true stationary rest frame, which means your boss's clock outside of your car would appear to run a little bit more than the clock inside your car. So, say it takes you 35 minutes normally to get to work. How much lateness can you blame on relativity itself? Well, if we want to calculate the improper time, or the time from an observer not moving with that clock, the improper time is going to be equal to the Lorentz factor gamma times the proper time of 35 minutes. And to calculate our Lorentz factor, the Lorentz factor is the square root of 1 over the quantity 1 minus our speed squared divided by the speed of light squared. So if we're traveling at 30 meters per second, and we divide that by the speed of light of 3 times 10 to the 8 meters per second, V over C is 10 to the negative 7. And if you were to try to use a calculator to calculate gamma, unless it can give you 20 digits of precision routinely, you're just going to get 1. And in fact, the easiest way to actually calculate this is to use an approximate method. We can take a series expansion of the term V over C squared as our x, and the quantity of 1 minus x to the negative 1/2 power can be expanded as 1 minus our power of negative 1/2 times our x V over C quantity squared, and then we would have to add in a correction term that would go like V over C to the 4th power. This is 10 to the 7 for V over C, 10 to the negative 7. We square it, it's 10 to the negative 14. We quadruple it, we're talking 10 to the negative 28. It's going to be tiny. This is a plenty good approximation. So 10 to the negative 14 times 1/2 gives me 5 times 10 to the negative 15, which means our Lorentz factor would be 1.00000000000000005. To put it in more practical terms, if I were to take this factor, 5 times 10 to the negative 15, and multiply it by 35 minutes, I end up getting an increase in time of 1.1 times 10 to the negative 11 seconds, which is 11 picoseconds. That is not a very, very, very large number at all, so you probably can't blame relativity. But if you could travel much, much, much closer to the speed of light, then you could observe a noticeable time difference. So say you wanted to drive for 35 minutes from your perspective, but for it to take 40 minutes from the outside world's perspective. Well, again, 35 minutes would be your proper time, so to find gamma, gamma would be equal to the 40-minute time that the other observer would record divided by your proper time, and 40 minutes divided by 35 minutes gives me 8/7. Now, if you want to take gamma and use it to find the relative speed compared to the speed of light, the relative speed compared to the speed of light is going to be the square root of 1 minus 1 over gamma squared. 1 over gamma squared is going to be 49/64. So you take 49, subtract it from 64, divide by 64 and take the square root, and that gives you a value of 0.484. So you'd have to travel at 48.4% of the speed of light to add 5 minutes to a 35-minute commute. But if you take a look at the distances, driving at 0.484 times the speed of light would take you a distance of 3 times 10 to the 11 meters. But an observer would say your car's driving for 40 minutes, also at 0.484 meters per second. That outside observer would say you're traveling for 3.5 times 10 to the 11 meters. That's a pretty big difference. It's a difference of 8/7. And the answer to that paradox is length contraction. Just as time dilates, length contracts. So you're driving 35 minutes through a squished-in space that's 7/8 the size of outside space. And folks, an outside space would see your car squished 7/8 of its normal size as you drive that 3.5 times 10 to the 11 meter distance. Thanks for watching.